Okay, so this is video 7, and I'm going to go through hints about each question on the worksheet. And the first thing I want you to understand is really this whole structure here. You see this a lot in math classes, and so I want you to understand what this means. So this means that you have some function, f of x, any old function you want, and it's going from, in this case, 0. The lower limit of integration is 0, and you're progressing up to some value x, okay? And actually, I should put a t here and dt because we're mathematicians. I say a physicist would not care that there were two different kinds of x's. That wouldn't bother a physicist, but it bothers mathematicians. So this axis would be t, and you're going from 0 to x, and you want to know what the area is under the curve, and if you can calculate that, that'll give you g at this x value. So this x value, this x value. So that's the role these things play, and as you move this x value along, so I can just do this by the magic of my computer, I can just move this along. As x moves, I'm expanding the amount of t that I'm taking, and so that changes the result. You should think of this f here as being your deposits and withdrawals from your bank, but then this whole sum is your total balance at the point at which the area. So like the area is your balance, right? Because your balance is the sum of all your deposits and withdrawals. Okay, now something that you want to realize when you're doing these problems and thinking about what all this means is if you change the lower limit to anything you want, it could be capital A, then this is changing to capital A. And this means that g of capital A is always 0. It's saying before you start doing anything to your bank account, before any deposits or withdrawals, then your balance is 0. Or another way to think of it is you're running balance starting at, like, how much has your balance changed since the start? Well, if you're looking at the start, then it hasn't changed at all since the start. So we often just put a 0 there, but it could be anything. It could be a -1. It could be anything you want, but that is your starting point. So don't let this confuse you, the fact that your starting point happens to be 0. Your starting point could be anywhere. Okay, and the other important thing is just mechanically. You need to understand this conceptually, but you also need to understand it mechanically. And so if f of x is your deposits, and then g of x is your balance, essentially, right? What is the derivative of your balance? It's your deposits. Okay, so you're back to where you started. You're just playing with these terms, really. And so when they're asking the question, where is g concave up? So I want to know the question, where is g concave up? Then you want to know, well, if g double prime is positive, how do you figure that out? Well, you take the first derivative of g and you get f. Okay, so then how do you know when the second derivative is positive? Well, clearly g double prime is equal to f prime, and that's enough hints for you. Okay, so I'm going to let you think about that. Okay, so for question 2, I want you to understand that this is a numerical question. So the structure of this question is f of x equals, again, this 0 to x, integral from 0 to x, and the thing inside is a function of t. So it's a messy function of t, messy of t dt. Okay, so the reason why we pick a messy function in there is because we do not want you to try to take the antiderivative. So you may look at that and just choke, but it's actually a gift because it's a hint that you're not supposed to be taking the antiderivative of that. And in your exercise it says approximate capital F of x at the following points, and you notice that they're evenly spaced. So if your messy function, whatever it is going from 0 to, let's see, you're supposed to go to 2.5, let's say, then if you're going from 0 to 2.5 and it's asking you for a whole bunch of just different approximations, well, of course we divide it, and then what? You can either do Riemann sums left and right, or average them, trapezoids. You have a whole bunch of options, but what you're going to do is you're going to bust this up into 5 different sections, and as you go along you're going to accumulate this. So you're actually going to calculate these areas, or approximate these areas in these 5 regions, and then for the first answer you're going to say, okay, capital F of x is F 0.5 is this whole area. Capital F of 1 is both of those areas together, and so forth. So you keep accumulating, you just calculate these and then add them together. So capital F of 0.5 would just be the area of this first region here. And capital F of 1 would be A plus B if this is the second region. Okay, so that's the structure of the problem, and that should be fine. You can also use Desmos, you can use other technology like Python. So let me show you that. Okay, don't forget how to use the lambda. Don't forget, if you're squaring in Python, it's a double star, and then you can easily evaluate those the height of that curve there. Okay, so that's I think that's enough hints for number 2. I think you can take it from there. Okay, question 3, I just want to give you this sort of visual in your head. A lot of calculus questions, well, we like to give you questions that are hard and easy at the same time. We really want to pitch conceptual questions that are not going to overwhelm you with the actual calculation of them. And so it's a recurring theme to give students questions that are from 0 to 1. You're integrating 0 to 1, and you're integrating, x squared, x cubed, square root of x, all these guys. There's all sorts of problems you can do while sticking to these very basic functions, and all of them intersect at 0, 0 and 1, 1. They intersect each other, so it's just a really easy thing to do. Now, just keep in mind that in quadrant 3 or quadrant 2, these things do different things. So you would have like even functions end up over here, odd functions end up over here, but if you're using like cube root or square root, then you're going to stay in quadrant 1 rather. So these are just things to keep in mind. So a lot of exercises are built around these functions. So in this specific question, I'm just going to give you the hints I think are the most commonly mistaken concerns for students. Is one of these functions is going to be above the other, and since there's square root and cube root, they're going to be concave down rather than concave up, which is if they were square or cubed. So you can kind of look in your mind, if this had been the x-axis and this had been the y-axis, which would it be? Well, in that case, this would be x cubed, so this must be the cube root of x because we flipped it, and this one must be the square root. But even if you mess that up, the calculus will save you. Right? So even if you can't remember which one is on top, and you can easily test this, but you're just going to integrate from 0 to 1 each function. So let me intentionally put it in backwards. Okay, so if I did this and you work it all out, you're going to get a negative number, and you're going to say, oh, I must have flipped them, and then you're going to go back and you're going to say, how are you going to fix that? You're going to probably just put a negative here and a plus here, and then when you're done, all your signs will flip and you'll be happy again. Okay, so just be very careful and systematic, and a lot of things, if you flip them in math, you just get a minus sign, and it's easy enough to fix that kind of error. So that should be a pretty straightforward problem for you. Okay, question 4, one of them you should just be able to glance at and immediately get the answer without thinking about it, and if that's not the case, that's okay. You're just going to do the same average value trick. Average value of f of x from a to b is just going to be this, integrate it and then divide by the width of that interval, and this is going to be your average over the interval. Okay, so really easy. Go ahead and calculate that, and again, you should find that one of them gives you a very obvious answer in retrospect, and that should help you. Okay, so for question 5a, you're supposed to be using the fundamental theorem. So don't overanalyze this. It should be pretty easy. And then b is basically a thinking question. If you're confused by that, you could do this numerically. You could go to Desmos or Wolfram Alpha to do a numerical estimate to see just a couple spot checks. The idea here is if you keep adding money to your bank account, but the amount of money you're adding is decreasing, you're still getting more money in your bank account, right? So it's just a standard trick to see if you're confusing the first and second derivative, or if you're confusing the function and its derivative. So that's why it's a thinking question. It almost is more confusing to word it than to not word it at all. Just sort of think in terms of what is the function, what is the derivative, what is the second derivative, what are they doing, and don't jump to an answer without thinking it through. And 5c is about concavity. And just remember, for a generic function, if the function itself, if the second derivative is positive, we get concave up, holds water. Second derivative is negative, concave down, spills water. So I like to think in terms of a circle, and if I have a circle here, I split it into 4 pieces, and then I think of it as being the 4 prototypical function bits. Here I have f prime positive, and here I also have f prime positive, so f prime is negative in the other 2 quadrants. But then in terms of second derivative, it's top versus bottom, right? So this guy is concave down, concave down, concave up, concave up. So those are the 4 ways you can combine first and second derivative, and just a really quick visual on that to help you keep your bearings on what's what. Okay, and I think that's it for our video 7. You guys should do fine on that, and I will see you soon.